I'm still trying to set up everything. It's like having a first class all over again. So. Okay, so let's start now. Let me just see if there's anybody in Zoom waiting. Oh, there's somebody still waiting. Right, so okay, so I have to do recording. So wait, okay, so there we go, record. Okay, so it's is it already recording? It's recording. Did you guys get a message saying it's recording or it's not recording? Oh, it seems to be recording. Do you see that it says that it's recording?
Yeah, your red dot is on, so.
Okay, good. So it is recording. Okay. All right. Okay, so. Okay, what else am I forgetting? So it's being recorded, lectures are there. Okay, so we can start. All right, okay, so welcome everybody. So my name is Professor Shomik Pal. I'm professor at University of Washington, and I'm co-teaching this with Professor Kim at UBC, who was teaching for the last 2 weeks. So if you're a student from University of Washington, I will also have my in-person office hours. That's tomorrow, every Tuesday from 1 to 3 p.m. at Padelford Hall. So drop by if you want to chat. If you are remote, and if you would like to discuss some material, just send me an email or a message over Slack, and I'm happy to discuss further. Okay, let's try. So let's start with this. So we are talking about optimal transport. Now, one of the things that Younghan and I do slightly differently is that Younghan by training is an analyst and I'm by training a probabilist. So some of our language and our notations are slightly different. This is good training for you because optimal transport these days are being used in lots of different areas. But if you are confused or you don't quite understand what I'm saying, please do let me know. Right. So last time, Youngman ended by talking about Brunier's theorem. So Brunier's theorem, this is the famous and one of the most important theorems in this subject. This is due to Jan Brunier, a mathematician in Paris. And it identifies optimal transport maps as gradients of convex functions. This is broadly the idea here that the solution of the Monch-Kantorowicz optimal transport plan are given by gradients of convex functions. So that's where we're going to start our class today. So I'll describe this in greater detail. The second thing that we're going to do this week is that once we have this identification due to Brunier, it allows us to draw so-called straight lines between two probability measures. So in other words, given two probability measures, a start and a finish, I can draw a curve, intermediate curve, where every intermediate point is another probability measure. And these are called McCann interpolations. And they're very, very important in this theory due to this idea which connects optimal transport to fluid mechanics. And also we'll get over this over the following lectures. And the third thing that I'm going to do is that we're going to talk about convex functions of probability measures. So we're going to talk about functions or probability measures that are convex along these straight lines. This was actually one of the goals of defining by these McCann interpolations done by Younghan and I, or our common friend Robert McCann. He invented this interpolation to make certain functions or probability measures convex, which are not convex under usual way that you would draw a line between probabilities. Okay, so that's the goal here. So I will also identify here, McCann refers to Robert McCann, who is a professor at University of Toronto. Okay, everybody can hear me clearly still?
Yes.
Yeah.
Okay, good. All right, so let's recall Brenier's theorem. So this is Brenier's amazing theorem. We're going to only talk about quadratic cost. There are other costs that you can generalize this to, but it's most powerful for quadratic cost and also the most useful. So we're going to stick to quadratic cost. So the problem is that I have my space is RD. I have two probability measures, mu and nu. And my cost function is this quadratic cost function, which is 1/2 norm of y minus x squared. Now, you might wonder, why have I put a 1/2 here? Well, that's because, I mean, it's a constant, and there are certain ways that you have to carry constant for later calculations. And if you put a 1/2 here, things become simple, especially when you're doing probability, and we'll soon bring Brownian motion into the picture. Things become simple if you put 1/2. So I'm going to write down my quadratic cost as 1/2 norm of y minus x squared. This should not cause too much confusion. Now, Brenner's theorem will assume that my initial measure mu has a density. Now, this is strictly not needed. There is a certain Hausdorff the kind of condition that is needed, which says that mu is not just atomic. There is some problems with atomic measures that we will see. But we're just going to assume that mu has a density. It means that it is absolutely continuous. So mu is absolutely continuous with respect to Lebesgue. So mu has a density. Then the theorem is saying that if mu has a density, there is a unique solution to both Monge's problem and the Kantorovich generalization of the problem. Both have the unique solution, and therefore they're the same. Moreover, this solution is given by a very special structure. Ky, sorry. I just got this iPad and I still don't know how to use it. How do I go back? Okay, so Brenner's theorem is saying that this unique solution has a very special structure. What is this special structure? There exists some convex function phi, which takes my RD, my underlying space, to the real line, but it also includes infinity. When you do convex analysis, it is typical that you include infinity. You allow the function to take infinite value. Of course, there's a related concept of what is the domain of this function, and the domain of this function phi is all the points where phi is actually finite. Now, this function is such that if you look into its gradient map, now if the function is taking from RD to R, its gradient is a map from RD to RD. And if you push forward your initial mu by this gradient map, you would get a nu. So the first statement of Brenier is saying that if mu is absolutely continuous and nu is any other probability measure, then there exists a function, a convex function phi, such that the gradient of the convex function will push forward mu to nu. That statement itself is non-trivial. Okay? Given two probability measures, it is not clear that there will exist some map which will transport mu to nu. Brenner's first statement says there exists such map, and that this map can be taken to be the gradient of a convex function. That's a remarkable theorem. First time. The second part is saying that once you find such a map, that is the optimal solution for both my Monge and my Kantorovich problem. So Monge's problem is asking for a map that would transport mu to nu, which is best among all maps with the quadratic cost. And this is this one, this gradient of a convex function. Now, Kantorovich's problem is asking for a coupling. It's asking for a coupling of mu and nu, which is the best among all couplings, also in the quadratic cost. So again, Youngman must have said this, but if I have a map, how do I produce a coupling? A coupling of the coupling xy this is going to be a very degenerate coupling where I put a delta mass at x and gradient of phi of x. So this is not a coupling which has a joint density, although mu has a density. Rather, it is supported on the graph of the gradient of a convex function. Good. So again, Breni's amazing theorem has several parts. One, it says that there will exist a gradient of a convex function such that it will map this mu to nu. And the second is that it's a unique solution for both Monge and Kantorovich problem. Now, I want you to understand that this function phi is not unique. That's not what Brenier is saying. What it is saying is gradient of phi is unique. This map of gradient of phi is actually unique. And therefore, the function phi could be unique up to translation. So I can add a constant 1 to phi, and it will still give me the same gradient. So it's not that the function phi is unique, it's actually gradient of phi is unique. There's a slight other measure theoretic condition that we'll get back to. It's almost surely unique, almost surely being because mu has a density, but otherwise it's fine, it's unique. Good. If you have any questions, please let me know. Speak up because I think it's hard for me to.
Can you let in the person in the waiting room?
Oh, there is somebody at the waiting room. Okay. Thank you for alerting me. There we go. All right. Okay. Thank you. Yeah. Sorry. Go ahead.
My question. Oh, sorry.
Yeah,
You can go ahead first.
Okay, yeah. My question is, should we also assume, my understanding is that we need to assume that mu and nu have finite second moments?
That's correct. Yeah. So I haven't assumed this. Actually, the convex function part, the fact that there exists a convex function doesn't depend on it. The other one does depend on it. It has to be optimal solution for the quadratic cost. The underlying assumption it has second moment, finite second moments. That's correct. Yes.
Right. So I actually had two questions. One,
Yes.
you mentioned something about geodesics before. Would that be kind
Yes.
of the way that you would try to interpret what the transport plan is doing? Would be and
You
that
will
would be
see. You will see. I will give a very
okay.
good logic of why this is how we are going to define geodesics. This is where the geometry is slowly seeping into the theory. You will see.
Okay.
Still,
And
yeah.
I apologize if I missed something, but this pi
Yeah.
xy, this is a transfer plan
This
on
is a transport plan on RD cross RD. So this is a joint. This is a coupling. This is a joint probability measure on RD cross RD.
yeah, I guess it was not easy to see why pi xy is equal to the direct delta x and
Oh,
gradient
no.
of
This
u
is just the
x.
definition. The
Oh,
definition
okay.
is that so this goes back to the idea of why is Kantorovich's problem a relaxation of Monge's problem?
Mm,
Because Monge's problem is asking for a map. But if you have a map, let's say the map is x going to x squared. Then you take an x, let's say in standard normal, and then you create a delta mass at x comma x squared. Then you get a joint distribution. A joint distribution whose first marginal is not standard normal, and the second marginal is chi-square.
mhm.
But it's a very degenerate coupling because it doesn't come with a joint distribution. It's entirely supported on the graph of the function x squared.
Oh, I see. Okay, thank you.
And
But I
so
think,
sorry, go ahead.
but I mean, to go on that question, I think we should be tensoring this delta mass with mu, right? Like, We can't just
Oh,
have the
yes.
delta.
Oh, yes. Sorry,
Yeah,
of course. I mean,
that's what I was
okay.
thinking as well. That's what I was
Okay.
thinking as well.
Okay.
Yeah.
Yeah, you're absolutely right. So this is, of
Okay.
course, what I wrote is something doesn't make sense. You're absolutely right. Yes. So what I really mean here is identity, gradient of phi, push forwarding, mu.
Oh, okay. Okay.
This
Thank
makes
you.
sense? Yes. Thank you.
Yeah.
Yeah. Any other questions?
Yes, I have a question. How do we
Yes.
make sense of the gradient at the points at which phi is infinite?
Yes. So all this is coming. So this is just a quick recap. All this is coming. So I will come to this very quickly. Okay. So let's start with an example here. So here's my first example. I want to transport normal 0, 1, which is my standard normal, to normal 1, 4, which is normal with mean 1 and variance 4. Now, if you're not familiar with the normal distribution, sometimes which is also called the Gaussian distribution, this is one of the most fundamental distributions used in probability and statistics. So normal distribution, the standard normal distribution has the following density, which is phi of x. This is 1 over square root 2 pi. I'm just doing it in one dimension, but of course, this can be done everywhere else. Z square over 2. And this is for z between minus infinity and infinity. It's a bit hard to explain if you have never seen normal 0, 1 normal distributions before, why it is so fundamental. One thing is the central limit theorem, things converge to normal distributions. But maybe all of you have already seen normal distributions. I don't need to spend time on this. Now, I want to transport normal 0, 1 to normal 1, 4. If you don't know what normal 1, 4 is, alert me and I'll write down the density too. Now, if you ask any statistician to say, okay, is there a map that would transport normal 0, 1 to normal 1, 4 or any other normal mu sigma square or normal a sigma square, there is always an obvious answer that people will come, because this is what we do repeatedly in statistics, which is that you take the map z going to 2z plus 1. So here z is random variable from normal 0, 1. So when you apply the map 2z plus 1, its mean becomes 1, which is from here, and that matches with this mean. And its variance become 2 square, which is 4, which matches with this guy. Now you look into this function, 2z plus 1. It is immediate that this is the gradient of a convex function. Why? Well, in one dimension, because it's an increasing function. In one dimension, it's increasing functions are always gradients of convex functions. But also, you can actually compute it. You can directly see that if I define my phi of z to be z squared plus z, it has a quadratic part z squared, which is convex, and there's a linear part which is just z, which doesn't change convexity. And therefore, phi of z is a convex function. Again, I want to repeat the fact that I could have added a 3 here, and that wouldn't change anything. It's not that the convex function is unique, it's that its gradient gives me the unique map, and its gradient is always 2z plus 1. Now, once I know that this map 2z plus 1 transports normal 0, 1 to normal 1, 4, and the fact that this is a gradient of convex function, we have solved the Monch-Kantorovich problem. Brennier's theorem is telling me this is a unique solution of the Monch-Kantorovich optimal transport problem. I don't need to do anything else. That's it. I just need to find this map. Good. One more example. Let's again take mu to be my standard normal 0, 1. And now this is not mu, this is nu. So let's take nu to be a very atomic probability measure, which puts mass 1/2 at 0 and 1/2 at 1. Okay, very, very atomic. Now, if I ask you, okay, give me a map that would transport normal 0, 1, a continuous random variable, to this discrete mass of 1/2 at 0 at 1/2 at 1, what would be your obvious answer? The obvious answer would be that, okay, if the normal distribution is negative, below 0, I would take the value to be 0. And if it is above 0, I would take the value to be 1. In other words, you would take the map to be the indicator that the normal random variable is greater than 0. Correct? Why does it transport normal 0, 1 to delta at 0 and delta at 1? Well, what's the probability the normal distribution is going to be, a standard normal random variable is going to be greater than 0? It's 1/2. That's when this is 1. What's the probability the standard normal random variable is going to be less than 0? Another 1/2. That's when this is 0. So switch on, switch off. So it transports normal 0, 1 to this 1/2 delta 0 plus 1/2 delta 1. Is this a gradient of a convex function? You bet it is. It's an increasing function, and the convex function I can pick to be the positive part of z. And now you see that I have a problem that phi is not quite differentiable at 0. But this doesn't create a problem. And you can see why. It has one point where differentiability fails.
Did we get that right? Should it be z greater than 1/2? Because you have delta 0, delta 1. They're not symmetric about the origin. It's not like delta -1 and delta 1.
Right. So if I say, okay, so I have z is normal 0, 1. And if I look into, let's say this is my t of z. So then t of z takes two values. Either it's 1 or it is 0. Right? Because it's an indicator random variable. And so what's the probability it takes 1? It's when the standard normal random variable is greater than 0. And so this happens with probability 1/2. What's the probability it takes 0? Well, when the standard normal random variable is less than 0. And that's with probability 1/2. And so T of z has distribution 1/2 mass at 0 and 1/2 mass at 1. I think this is my delta mass. So here, does this make sense?
Yeah, thank you.
Okay. All right. Okay. So now why doesn't it create a problem that phi is not differentiable at 0? Is because the set where phi fails to be differentiable, which is this origin, has measure 0. And my normal 0, 1, being absolutely continuous with respect to Lebesgue measure, never takes the value 0 or takes the value 0 with probability 0. And therefore, it doesn't really create a problem if I take indicator z to be greater than 0. Is that clear? So, and similarly, I could have taken indicator z greater than or equal to 0 to be another solution. This would also do the same transport. It will also give the same cost. Does it contradict uniqueness? Well, that's where measure theory comes in. It's unique, almost surely mu. Are you following what I'm saying? So the function is not unique.
Yeah.
The gradient is not quite unique, except that the map is unique almost everywhere. That's the uniqueness of part of it. All right? Okay. Now, this problem, as one of you said, that there's a problem, what happens the function is infinity, what happens the function is non-differentiable. These are very important problems in convex analysis. And so typically, when you do convex analysis, you don't really talk about derivatives, you talk about subdifferentials. And I want to talk a little bit about subdifferentials because one, it is very important for doing proper convex analysis. And two, this is an idea which will carry over when we do the geometry of the Wasserstein space as well. So brief detour into this idea of subdifferentials. So I'm going to take a function phi, which is a function on my RD, which is going to be convex, lower semi-continuous, and proper. Now, everybody knows what convex is. Everybody knows what lower semi-continuity is. It doesn't have to be continuous, just lower semi-continuous is enough. What does proper mean? Well, what proper means is that phi, so here proper would mean that phi must be always larger than minus infinity. And phi cannot be always infinity. And phi, so the phi of x must be less than infinity for some x. So very, very mild condition. I can't just take a minus infinity function. It can never take the value minus infinity. And it can take the value positive infinity, but it must take somewhere finite. Okay. Now, given a point x in the domain of this function, where this function takes a finite value, I'm going to define a set-valued map. So x is in the domain of phi. X is in the domain of phi. So del phi of x, this is a set. This is not a point. This is a set. In fact, this is a convex set. We say that a vector y is in this set of subdifferentials of phi at x. That's a proper way of saying this. If and only if, for all other z, I must have the property that phi of z is greater than or equal to phi of x plus y dot z minus x. Okay, how should I think of this object? As you know, that a convex function is basically given by the property that the curve of the graph of the function lies above the tangent. Okay, so this is my tangent, and the graph is lying above the tangent. If there's a unique tangent, then that's fine. That's not the problem that we are trying to solve here. The problem is with functions like this, when there is no unique tangent. And then I want to say that no matter what kind of tangent I pick, and y is this angle of this tangent, the graph lies above this line. So whatever angle satisfies this, I pull them together, and that's what is my subdifferential of my function phi at the point x. Is this clear? In fact, let's take this example of the absolute value of x.
So is this sort of defined point-wise, or are we saying that this condition needs to hold for multiple x's in the domain phi?
No, I'll come to that. So fix an x. For every fixed x, the set of subdifferentials is a set y of all y, such that for every z, phi of z is greater than or equal to this, which means that the entire curve lies above the line with slope y, which touches the curve at x. Okay, so that you look at all this. Okay, let's look into this particular example. This is my function of absolute value of x. Okay, let's take 3 points here. The origin, which is 0, 1, and -1. Can you tell me what is the set of subdifferentials at -1? What is my subdifferentials at +1? And what is my subdifferential at the origin? Let's ask this question. So if I look into -1, I'm saying what are the lines that I can draw which will touch the curve at -1, the slopes of these lines, such that the entire curve of absolute value of x are always going to be above that line. Can anybody tell me what's the answer for this?
So maybe I'm misinterpreting. So you're saying it's the slope of the lines that are like lying below, right? So
It's the slope of the lines, exactly.
Yeah.
It's all the collection of slopes.
So
So
this
what is
one
what is it at -1?
should be just -1, right?
Should be just -1, exactly. So this is a singleton, which is just -1. What is the the subdifferential set at +1? +1, just a singleton +1?
Just one.
Yeah. I hope you're understanding this, right? At +1, if I take a line at slope 2, then obviously the entire curve is not going to line above the line, because to the right side of 1, the curve will be below the line. Okay, so now for the final thing. So this part is kind of easy. What is the set of subdifferentials at the origin? So what are all the slopes such that the line with that slope will lie below the curve?
the set -1 to 1
Exactly.
inclusive?
So exactly. It's just a closed interval -1 to 1. Exactly. Perfect. And so that's the idea of the subdifferentials. You don't want to assume differentiability. You just want to collect everything such that if you draw a line with that slope, it lies below the curve. One thing you notice is that this curve, this set -1 to 1 is convex. And that's always the case. This is always a convex set. And that just follows from the definition. You can verify that this is convex. Now, the set of all subdifferentials, which is the important thing for optimal transport, is all pairs x and y such that y is in the subdifferential of the function at x. Okay, this is a graph of subdifferentials. Okay. Now, sorry, go ahead.
Yeah, I had a question. So if the function is differential at that point,
Mm-hmm.
then the set of subdifferentials at that point is just going to be the derivative at that
That's
point.
exactly correct. And that's my next slide. Yeah, so that's
Okay.
exactly my next slide. It's exactly correct, but this is kind of obvious from this picture that if the function is differentiable at a certain point, the subdifferential exactly becomes a singleton and it just contains the gradient. Okay. All right, good. So the set of subdifferentials, the graph of subdifferentials has a very, very strong geometric property. And it is called monotonicity. Monotonicity says that if I have 2 points, x1 and it's a subdifferential y1, and x2 and its subdifferential y2, it must satisfy that this dot product is non-negative. So y2 minus y1 dot x2 minus x1 is non-negative. All right. So arbitrary vector fields cannot be gradients of convex functions. In one dimension, this is obvious. In one dimensions, we know that what can be gradients of convex functions is that increasing functions. And increasing functions obviously will satisfy this property. If y is an increasing function of x, y2 minus y1 dot x2 minus x1 has to be non-negative. Now, when you go to multi-dimensions, the concept of increasing functions is no longer there. However, this functions of monotonicity is there. That if I have y2 is that if I take any gradient, the inner product of y2 minus y1 and x2 minus x1 must be non-negative. Are you following this? How do I prove this? The proof is easy. So if they are both subdifferentials, so y1 is in the subdifferential of x1, so I would get that phi of y2 must be greater than or equal to phi of, not phi of y2, but phi of x2 must be greater than or equal to phi of x1 plus y1 dot x2 minus x1. And phi of x1 must be greater than or equal to phi of x2 plus y2 dot x1 minus x2. All you do is just add this up, cancel phi of x2 plus x1 from both sides, and you have this inequality. You see this? Now, this is fundamentally connected to optimal transport. And we'll see this later. Why this is fundamentally connected to optimal transport, I'll go over this. It is related to the question is, does this kind of monotone vector field characterize convex gradient? In other words, if you have a vector field which always satisfies this kind of monotonicity condition, does it mean that there is a convex function whose gradient is given by this vector field? The answer is almost, but not quite. This one does not, but there's a slight generalization of it, which is called cyclical monotonicity, where it has to hold not just for y1 and y2, but you have to add any finite length of such vectors and suitably add them up. and then it has to satisfy this. I will spend some time later to show why this is thing. This is just an optimal transport between atomic measures. And it's a beautiful demonstration of how geometry and optimal transport are related. Okay, we'll come back to this. Is the definition of subdifferential clear?
Yes.
Good.
Can I ask how
Yes.
the monotonicity would extend to manifolds? Like where you're not able to directly compare your
Right.
points and
So
differentials.
this is a bit difficult to explain. In manifold, of course, you cannot quite do a thing. However, there's an extension of Brunier's theorem for optimal transport on manifolds. And this is the work of Robert McCann, where what it does is that it does this monotonicity on the tangent spaces, and that you can generalize this. So that's one way of doing this. The second way is actually what we are going to pursue. The second way, what we are going to pursue is because we are going to think of the space of probability measures itself as a manifold. In fact, it's a Riemannian manifold. And we'll talk about gradients there. We'll talk about convex functions there. And you will see it has some resemblance with this kind of monotonicity. But this is really about linear structures. You can do it over RD, you can do over Hilbert spaces. It doesn't exactly transport to manifolds which have curvature.
Okay, thanks.
But I'll post the paper by Robert, and you can see how it is generalized to manifolds. Okay. All right, good. So some other fantastic properties of convex functions are that, okay, so this is one of you already pointed out, that a easy way to see that a convex function is differentiable at x is to look into its subdifferential set. If it's a singleton, then it is differentiable, and that singleton must be the derivative, the gradient. It is, again, it's a simple analysis that the gradient must always be contained inside the subdifferential. It is actually a deeper theorem. You can find this in Rockefeller's book, that any convex function is locally Lipschitz in the interior of the domain of phi. Okay, so let's go over this term. So what is domain of phi? It's all points such that phi is finite. What is interior of that is the largest open set that is contained inside this set. What is locally Lipschitz? It means if you take any compact subset of that, and over that compact subset, you can find a constant such that it's Lipschitz with that constant. Good. Now, by Rademacher's theorem, any function that is locally Lipschitz is differentiable almost everywhere. And therefore, I immediately get that any convex function is differentiable almost everywhere in the interior of the domain of phi. Therefore, if my mu is absolutely continuous, I should not worry about the gradient of phi, writing gradient of phi, because gradient of phi may only be defined almost everywhere, but the push forward by gradient of phi of mu is uniquely defined. This is a measure, and this measure is uniquely defined, and that's because measure theory. Is that clear? Why do I only have to restrict myself to inside the domain of phi? Because outside the domain of phi, I don't have this concept of the subdifferential. So nothing I'm going to talk, no transport problem that I'm going to talk about will include a function where I'm transporting something which is outside the domain. So it's always inside. Clear? Okay. Now, the other thing that you must understand about subdifferentials is its deep, deep connections with convex conjugates. It's one of the previous classes I commented that when you do convex analysis, you should not, or at least you should try to avoid use Newtonian calculus as much as possible. That's not the way that you do convex analysis. You do convex analysis by using subdifferentials and convex conjugate. So let's try to understand this convex conjugate here, how it is related to subdifferentials. This is the definition of Legendre transform, the Legendre-Frenchel transform, or what is called the convex conjugate. Legendre-Frenchel. Oh, sorry. Not shell. Okay. So if I have a convex function, phi, I can define its convex conjugate phi star of y by this formula. This is the supremum over all x dot y minus phi of x. And you may have seen this picture. I can't remember, must be there. Okay, this is my convex function. I draw a line with slope y, and I look into the maximum deviation between the line and my convex function. This is my phi star of y. Once I define my phi star of y this way, my phi star also becomes a proper lower semi-continuous and a convex function. So the convex conjugate preserves the set of convex functions, a proper lower semi-continuous convex function. The thing that you should always remember, this is the important thing, is this inequality, which is that for any pair x and y, x dot y, the inner product, is always less than or equal to phi x plus phi star of y. Why? Well, the answer is right here. Phi star of y is the supremum over all x dot y minus phi of x. So in particular, for any given x, it must be greater than or equal to, because it's a supremum. Once it is greater than or equal to, take this phi x, bring it to the left-hand side, and you have this inequality, x dot y is less than or equal to phi x plus phi star of y. But this is nothing but duality in convex analysis, in optimal transport. And again, I'll come to a proper statement. The other thing that you should remember is that if my phi I already start with proper lower semi-continuous and convex, then phi is its own double star, which means I start with phi, I do one conjugate, then I get phi star, I do another conjugate, I get another proper lower semi-continuous convex function. But if I start with already one, then they are the same. Okay, so a double star brings you back to this own function. This is sometimes called double convexification trick. Again, it's used in multiple proofs. Very, very important fact. Okay. How are duality and subgradients, subdifferentials related? It's by this fact. The following are equivalent. For any x and y, my x dot y is less than or equal to phi x plus phi star of y. But there will be some points, x and y, some pairs, where x dot y is actually equal to phi x plus phi star of y. What are those points? This can happen if and only if y is a subdifferential of the function phi at x, or x is a subdifferential of its convex conjugate at y. They're equivalent. You prove one of these and the other two follow. Is the statement clear? Okay. So subdifferentials by this property is characterized from this inequality. X dot y is always less than or equal to phi x plus phi star y. This is true for all pairs x and y. There is nothing special. But once they become equal, look at this condition. I'm just trying to see whether this inequality becomes an equality. That's it. No calculus, no derivatives. Once I prove it equal, that's it. Y must be a subdifferential at x, and therefore if phi is differentiable at x, y must be the gradient of phi of x. X must be the subdifferential at phi star of y. And if phi star is differentiable, then x must be the gradient of phi star. I want you to appreciate the fact that I'm getting information about the gradients via an inequality here. Okay. Okay. Now back to the full force of Brenner's theorem. So Brenner's theorem actually comes with two parts of it. The first part sometimes goes by Knott-Smith. Okay, one of you, when you come to my office hour tomorrow, will teach me how to use an iPad. Okay, so Knott-Smith, and the second part is Brenner. And it says the full force is the same. So again, I have my quadratic cost optimal transport. Now, for any mu and nu, it doesn't have to be absolutely continuous. For all mu and nu, I have a plan, pi, which is a solution of the Kantorovic's problem. It is an optimal plan if and only if the support of this plan is contained inside the graph of a subdifferential of a convex function. Okay? That is, pi almost surely, you must have x dot y is equal to phi x plus phi star of y. Okay, so let's see again what I'm saying. You don't have to assume mu is absolutely continuous. Mu can be any arbitrary probability measure. Mu can be any arbitrary probability measure. I'm always working under the assumption that everything has finite second moment, and I'm doing my optimal transport. A plan is optimal. There's a necessary and sufficient condition. It is that the support of this measure, pi, must be inside the graph of a subdifferential of a convex function phi. How are these graphs characterized? Well, that's what I talked about here. They're characterized by an equality, which means x dot y is equal to phi x plus phi star of y, which means pi is optimal if and only if you can find a convex function phi such that pi almost surely x dot y is equal to phi x plus phi star of y. Isn't that crazy? Has to be so. There's no other way. This is actually nothing but complementary slackness in a different language. So Younghan talked about complementary slackness in linear programming, that optimal linear programs must satisfy the primal and dual problems. They have this complementary slackness. If one is zero, the other must be positive, something like this. And here it is showing up. Pi is almost surely means that the measure pi has positive mass in this set. This is my slack. And he's saying that the slack must be exactly zero. So x dot y must be phi x plus phi star y. Now, when does Brunier come into play? Brunier comes into play that if I additionally assume that mu has a density, then almost surely over the support of this mu, then I have a gradient. If I have a gradient, then pi is unique, and it is given, and my pi is given by this identity, this transport, which is identity plus gradient of phi pushed forward by mu. And additionally, the support of my measure nu is a closure of the support of mu pushed forward by gradient of phi. Okay, any questions on this? Do you understand what I'm saying? Okay, you guys are okay still?
Yeah, I don't quite get. Yeah, this one's a bit harder to follow than the previous stuff.
Okay, can you tell me which part you would you're having more confusion about? I can go over that again. Okay, let me show an example first, and then maybe
one is just the structure of the statement.
Yeah.
Like it's I'm not sure where the equality of x dot y fits in, if that's like implied, or if that's part of the condition. Just even the structure of the statement is a bit unclear.
Okay, very good. So let me go over this again. Where is this equality coming into play? It's like this in this graph statement. So this graph, this is a subset of RD cross RD. So this is a subdifferential set. This is a subset of RD cross RD. How are these characterized? It's characterized from here. Y is in the subdifferential of phi at x if and only if x dot y is equal to phi x plus phi star y. And so this graph essentially consists, this graph of the subdifferential consists of only of those points where x dot y is equal to phi x plus phi star y. It doesn't have anything else. And so if pi, the support of pi is contained inside this graph, then pi is living inside this graph. And so pi almost surely I must have this equality.
Mm-hmm.
Okay, so that's the first part of the statement. The second part is just Brunier. It says that if mu is absolutely continuous, I can forget about subdifferentials. Almost surely I have a unique subdifferential, which is the gradient, and the push forward is giving me my transport. Okay, let's see an example here. So a counterexample to, well, I doubt a counterexample. It's an example of the first part holds, but the second part fails. That's what really what I'm trying to say. So here is an example here. I'm trying to transport my delta mass at 0 to this two atoms. So a half mass at 1 and a half mass at -1. Okay. If I ask you this question, okay, transport a mass of 1 at the origin to half mass at 1 and half mass at -1, what's the only possible transport that you can think of? You're going to split the mass at 0, send half of it to 1, and send the other half to -1. Right? There's only one way of doing this, which means that there's only one transport plan, and that must be the optimal one. Well, I mean, these are, okay, there is clearly the independent one and so on, but this is the optimal one, obviously, which is that you put the mass 0, you take the mass of the point 0, 1 to be half and mass of the point 0, -1 to be a half. Is that clear to everybody? That's the only way that you can do this. Okay. Okay, this is optimal. It clearly cannot have a Brownian map, right? Because if I have any Brownian map, then I would be transporting my random variable, which only takes the value 0 with probability 1 via a map. So the push forward can only take only one value, that is t of 0. But I want to push forward it to a measure that take two values, 1 and -1. So Brownian map does not exist. You need some absolute continuity kind condition. But the first part, that it is optimal if and only if it's in the support of the graph of a subdifferential of a convex function, still holds. So here is my pi. What is it supported on? It's supported on 2 points, 0, 1, the pair, and 0, -1, the other pair. Can I find a convex function whose subdifferential is a superset of these 2 points, 0, 1, and 0, -1? There are many choices. Here is one. I take my function phi x to be the absolute value of x. Okay. Then, as I already discussed in a few slides back, at the origin, my subdifferential set at the origin is given by the closed set -1 to +1, which means 0, -1 is a pair inside the subdifferential set, and so is 0, +1. And therefore, you see that the supporters pi is contained inside the graph of this gradient of phi, subdifferential at phi, and therefore this is optimal. Do you guys follow what I'm saying here?
Yeah.
Okay, good. So that's the full strength of Brownian's theorem, that it's optimal if and only if the support of the plan is contained inside the graph of subdifferentials. And this is unique if mu is absolutely continuous, where everything boils down to taking a gradient. But the lesson you should learn here is that if you're trying to solve an optimal transport problem for the quadratic cost, your goal is to find a gradient of a convex function that does the job. It's a problem to find the right convex function. Okay, good. Now we come to curves. McCann interpolations. So from now on, I'm going to assume that my initial probability measure is absolutely continuous. This is strictly not necessary. There is a way to bypass many of the things, but there are two reasons why I would do this absolutely continuous. One is that I will write my Brownian map to do all my things. It makes my life very easy. And in any high-level proof that you would like to do, you need to assume it absolutely continuous as a first step, and only then approximate arbitrary measures that you can try to do it. And because I want to keep it at a lower level of proofs, I'll always assume absolutely continuous. So absolutely continuous quadratic cost, I'm going to assume that, okay, from Brownian's theorem, I have a Brownian map that is transporting mu to nu, and this Brownian map is unique, and it is given by some gradient of a convex function phi. Now, so if I have a point x, I am transporting it to a point t of x over here. But then nothing is preventing me from drawing a line joining x and tx. I will come to that. Why would you like to do it? But let's try to do it. So for a t between 0 and 1, define another map capital T of small t of x, which is the intermediate point, which is 1 minus tx plus t of capital T of x, or sometimes it is written as x, which is my initial point, plus t times t capital T minus identity applied to x. Okay. Very simple. I'm taking x to t of x. I'm drawing them by a line. And if I am moving at speed 1 at point time t, where am I on this line? Well, that's my t of x. Okay.
I know in the beginning you mentioned that
Yeah.
the marginals are both in RD,
Yes.
and now we're really seeing like that the statement doesn't, the interpolation doesn't make sense if they're in different dimensions. But
Very good.
is
Yes.
everything we did only well defined, like with the gradients, if they're both in the same dimension, or does some stuff hold if one's in RD and one's in like RK?
So very good question. So Brunier's theorem and not Smith, as I've written down, they're only from RD to RD. Let's say, suppose you want to transport from RD to, let's say, R. I want to transport, let's say, normal zero identity in R2. So identity being a 2x2 identity, to normal 0, 1 in R1. There you can clearly see that even though normal 0, it's absolutely continuous, it's not unique. Because if xy is normal 0 identity in R2, x is normal 0, 1, y is normal 0, 1, they're both gradients of convex functions and they're both transporting. So clearly the uniqueness, Brunier's theorem, they don't quite hold. Some things can be said, it's more delicate. But again, I'll post a paper by our friend Brendan and Robert. And actually, Brendan Pass has done several works on this who actually analyze this. Not everything can be done, but this is again an area of active study, which is sometimes called, if you search by optimal transport between unequal dimensions, you'll get some relevant papers out of it. Yeah. So yeah, so Brennan's theorem will break down, but with some twist, some things will hold. Okay, so the thing that I want to say here is that there is a curve here, which is my geometry in my underlying space. I have a point x, I have my point t of x, I'm drawing a line in Euclidean space. Optimal transport will take a geometry in the underlying space, which in this case is Euclidean, and transform it to geometry in the space of probability measures on that space. How? By push forwards. So given my t of t, I will define my rho t to be the push forward of mu by tt. Now that's a measure. That's a probability measure. What is it saying? Well, I'm sampling my x from mu, and I'm push forwarding it by capital T of t. I'm looking into what's the distribution after time t if I move along this line. Now that gives me a curve on the set of probability measures. And this curve is called the McCann interpolation line from mu to nu. Good. So what is a McCann interpolation? It's a curve of probability measures going from mu to nu. How is it defined? Well, through Brunner map. You define a Brunner map that defines a flow on RD. And now you define a straight line joining the initial and the end point, and it defines intermediate flows. And then you push forward your measure by these intermediate flows, and it defines a curve of probability measures. That's my McCann interpolation. Good. Why would we do it? I'm coming to this. It's a very, very important concept. I'll see. But let's see an example. Here's my again example. So I take mu to be RD is my D is 1. So everything is on the real line. So my mu is standard normal. And my nu is normal 1, 4. What is a transport Brunner map between two normals? It is always an affine function. Because I always know that an affine function will transport a normal to another normal. Affine functions are always gradients of quadratic functions, and therefore by Brunner's theorem, they are the unique optimal map. So if I want to transport normal 0, 1 to normal 1, 4 by an affine map, the map is obvious, it's 2x plus 1. Because then the mean becomes 1 and the variance becomes 4. So what is my intermediate maps? My intermediate maps is x plus t minus identity times t. And if you solve it, it gets 1 plus t times x plus t. So what is my Macquer interpolation? I will take my initial source measure, which is normal 0, 1, and I will push forward it by this map 1 plus t times x plus t. So x is my random variable. So x is coming from normal 0, 1. What do I get? Well, the mean of x is 0. So the mean of this push forward is t. The variance is the coefficient of x squared. That's 1 plus t squared. And therefore, rho t is normal t comma 1 plus t squared. Is this example clear? Okay. At t equals to 0, I get back my normal 0, 1. At t equals to 1, I get back my normal 1 comma 4. At every intermediate step, notice what is happening. The normal shape is preserved. If I ask you to say, okay, this is my normal 0, 1, if it's my normal 2, 4, you can just take a linear combination of the two densities. You can just take 1 minus t mu plus t times nu as just adding the two densities together. A convex combination of probabilities densities will remain probability density. But that density is not going to be normal. It's going to be a bimodal density. It's not a normal density. The shape is not preserved. But Macquer interpolation will preserve the shape. What it is effectively doing is clear from here. You're going from 0 to 1, and it is having an interpolation in the mean, 0 to 1. You're going from 1 to 4, and it is an interpolation between the variance, 1 plus t squared. In fact, if you look into standard deviation, it's just a linear interpolation. And so it is interpolating between normals, two normals, while keeping in mind the statistical parameters that we all care about. And it's just a nice interpolation between the parameters, and the shape is preserved. This is the reason. Yeah, go ahead. Sorry, go ahead.
Is there some other simple distributions that stay in the same family? Because it seems really related to pathologies and variational inference, where you fix a family and you're...
You're absolutely correct. This is why a lot of people work with normal distributions and variational inference in using optimal transport theory. But here's my second example, which is another example. So I'm here. So you guys are just anticipating my next slides, which is great. So here's another example. I want to transport a uniform distribution on the d-dimensional cube to another uniform distribution on the d-dimensional cube, but the first one is a unit cube, and the second one is not a unit cube with side lengths are r. Is that clear? So this is my cube. So I take one cube, which is unit cube, and then I take the other cube, which is inflated by r, and so I get this uniform distribution between these two cubes. Okay, let's ask this question. What is my optimal transport map that transports this uniform to that uniform? The answer is again obvious. It is clear that if I sample a uniform from the unit cube and I multiply that vector that I get by the scalar r, I would get the uniform into this r cube. Right? If you're a probabilist, uniform from a cube is simple. You just sample d many IID uniform 0, 1, multiply each one of them by r, you get d many uniform 0, r, and therefore it's a uniform distribution on the d-dimensional cube with side length r. Is this optimal? Yes, of course, because it's an affine map. Every affine map is a gradient of a convex function. It's optimal by Brinier. What are the intermediate ones? So I'm going to join the line between my identity and Rx, I scale. And so it's a map which is also a scale, but now I'm scaling by 1 minus t plus tr. Right? What happens if I push forward my uniform over a cube by my affine map? Again, I would get a uniform map. Why? Because uniform over the cube is just d-IID uniform 0, 1. I multiply each one of them by a scalar factor. I remain d-IID uniform of some other length. And so rho t now becomes a uniform distribution over a cube with side length is 1 minus t plus tr. Again, the shape is preserved. If I'm going to go from unit length cube to the cube of length 2, I'm just expanding the cube from 1 to 2 at a certain way. I always remain a cube. As you can see, these are very special examples, normal, cubes, geometric examples. This is not going to be true for all examples. Most examples, the shape will have some distortions. But the reason machine learning people love this is that most of the time, let's say you're trying to transport something of the shape of a chicken to something of a shape of a cow, then the intermediate ones would look like half chicken and half cow. And if you search online, you'll find such examples. So shapes are very much preserved. Does it answer your question? Are there other questions?
What about like exponential family distributions? Any other simple ones can be worked out?
Right. So exponential family distributions, well, not always. So they are tricky. I mean, exponential is, of course, a very big family. I mean, it contains everything. So no. One-dimensional distributions, you can always solve for it, and I'll talk about this later. Multi-dimensional exponential families, no. I wouldn't say there's any neat formula for that.
Is there
No.
any special multimodal distribution that stays in the same family, even if there's a lot of assumptions?
That's a good question, but I don't know. Actually, I'll come to this. I mean, this is actually what we're asking is whether a certain family of distribution is convex in the Wasserstein space, and I'll use this terminology. So it's checking for convexity is a big problem, and I don't think there's a very clear answer. Sometimes it's known, sometimes it's not known. Okay. But you should, again, think of these McCann interpolations as like drawing lines between probability measures or line segments. And you are basically asking, oh, if I take 2 points, if I draw a line segment, does it remain inside the set? In Euclidean geometry, that is asking for convexity. And in this case, this would be looking for what is called geodesic convexity is where we are going. Okay. All right, very good. Okay, now we come to the point that why are we even calling this geodesics? Like, is there really a geometric way that we can think of these McCann interpolation lines so that we can talk about actual geodesics? The answer is yes. Well, so far we have talked about optimal transport as like, okay, I'm going to dig some hole from here in the ground, and I'm going to transport it into some mold. So a point X here will go to some point Tx over here. But there is, we are not living in Star Trek universe. There is no instant transportation from X to Tx. I will actually have to get a truck and carry my load from the point X to from the point Tx. And so I might as well ask the question in terms of dynamics. That suppose I have a seek of flows, and here this flows just means map. Some C of t is some time index map from 0 to 1. Such that at time 1, I've pushed forward my mu to nu. And I have a cost which depends now on the entire path. So t of x is where is my dirt that I initially dug up from X at time T, given that I know that at time 1, it's going to be in this mold, which is of shape nu. And so instead of asking like, okay, what is the cost between 2 endpoints, I might say, okay, what is the cost of the entire transportation path? And can I minimize this over all such paths? Right? That's an idea of dynamic optimal transport. Now, this is a problem of optimization over paths. This is why it's called dynamic optimal transport. And obviously, this is a more complicated problem because now I'm saying I'm not just optimizing over the endpoint maps, but I'm also optimizing over all intermediate points. In general, this is a very difficult problem and we can't quite solve it, but there are certain cases where our natural physical intuition should help. And this is one such case where my cost of transport is basically the total acceleration or the kinetic energy. So if x is going to tx and at an intermediate point, I'm going to say this is my zt, then I can measure the total cost of transport by looking into the z dot t, which is the velocity, norm square of the velocity, and integrate it. This is my total kinetic energy of the path. And from physical intuition, it makes sense to say that, okay, among all differentiable paths from mu to nu that transports mu to endpoint nu, what is the path that has a minimum kinetic energy? Right? Makes complete sense. In this case, and okay, so if I can solve for this, then if I look into my rho t, if I can solve for such t of t, I can define my rho t to be the push forward of tt from the push forward of my initial measure mu by this intermediate point t of t. And that tells me that as this ditch is being transported to this mold, what are all the intermediate shapes that I'm getting at different time points t? And the answer is that for kinetic energy, these are my Macan interpolations. So in fact, when mu is absolutely continuous, if I want to solve my kinetic energy, the minimizing kinetic energy problem, the solution is actually that you should join by a straight line between your initial point and your terminal point. Not a great mystery. This just comes from our basic physical intuition. If I'm trying to transport a x to t of x, why would I go from all the way like a zigzaggy way to go here when obviously I will save energy if I want to come directly from x to t of x? This, of course, assumes that all my paths are possible. I mean, there could be that there's only one road that is transporting x to tx, and that road is zigzaggy, but that's not the consideration here. Among all possible paths, what's the best one? Obviously, as the crow flies. That will minimize energy, and that should be the solution of the dynamic optimal transport problem. So it is given by this, and that's just a Jensen inequality calculation. And in that case, all my intermediate shapes are my Macan interpolants. So my Macan interpolations. In fact, you can prove that Macan interpolation by this definition, it's a geodesic. And again, this is a theme we'll develop over the future classes. And it is a constant speed geodesic. What does that mean? Is that if you follow along the Macan interpolation, if you compute the Wasserstein 2 distance between rho t and rho s, this is the optimal transport distance with the quadratic cost. It is exactly the t minus s times the full Wasserstein distance between the two endpoints. Okay, this is a property of constant speed geodesics that it's like you're moving at a constant speed, so the total distance just gets scaled. If I'm asking, okay, I want to go from 0 to 1, it takes me time 1 hour. If I'm moving at constant speed, where will I be after half an hour? Well, exactly at the midpoint. It's a constant speed geodesic. Okay, I think I will stop here, but do you guys have any questions? I'll talk about generalized geodesics next time. Do you guys have any questions in this class so far?
I have a question.
Yes, go ahead.
So, looking at the moments, basically you were looking at with these interpolations, how the mean and the variance are interpolated. So
that's for the normal. That's only for the normal. That doesn't happen elsewhere.
Okay, sure.
Only for the normal distribution.
Okay, has there been work done about basically how the moment generating functions interpolate, given some interpolation of measures?
You can, they are not always very friendly. I mean, for the normal, everything works fine because the Brenier map is affine. Even for the normal distribution, let's say you want to transport a normal mu1 sigma 1 in some RD to some another normal, which is mu2 sigma 2. It's an affine function, all right, that will transport to this one, but it's not an easy affine function. There's a certain, there's something, if you search online by Burus map, you get the answer to this, or Burus-Wasserstein. It's a pretty complicated map. And so for other distributions, like say you want to transport, I don't know, like a T distribution, a multidimensional T distribution to normal distribution, something like this, it's a complicated map. They don't, unless you have some concrete information about the Brenier map, it's hard to exactly pin down how other properties behave. So it's not always easy.
Sure.
Any other questions?
I guess I got a little bit confused by does like kinetic energy, does that have a specific meaning?
Right. So, I mean, it is exact meaning that you would associate kinetic energy with every path. You're basically associating a kinetic energy to be the cost of the path. More kinetic energy, you are spending more time and energy. Less kinetic energy, you are being most efficient. If I change, let's say, norm zt squared to the norm zt power 4, norm of dot zt power 4, it will be a different notion of energy. But the kinetic energy is the most relevant one physically, and that's what is related to this fluid dynamics that I'm going towards. So it's related to transports of fluids.
Okay, thank you.
Any other questions?
I think we touched on this before, but
Yeah.
the fact that these geodesics are straight lines, is that following from the fact that we're assuming a Euclidean metric? I think.
No. So okay, I want to stop you. Let's characterize a little bit here. When I say that geodesics are straight lines, these rho t's are not straight lines. On the space of probability measures, there is no straight line per se. What are straight lines are how the particles are moving. At some point, Young had talked about particles. So you should think about like particles, which are originally whose empirical distributions is like mu, and every particle is moving along a straight line to an empirical distribution which is nu. So what is straight line in the Euclidean space gets lifted on the probability space as Macan interpolations. So the straight line intuition is coming absolutely from the Euclidean space. There is no straight line over probability measure. That's one. Second, does the Euclidean metric important? Yes, Euclidean metric is important, but there's another thing which is actually important here, which is this quadratic cost. This straight line kind of behavior is also true for other convex cost, like if it's like y minus x to the norm 4, that's a convex cost of the endpoints. That's also would give you straight lines. But if you go beyond them, they may not be straight lines. And there are examples that peculiar examples of cost functions where they're not straight lines. There are other curves, and these are called Lagrangians. So you want to. In general, you can't solve them, but there's a certain physics problem where they come with some natural cost over paths where you can solve them. And let's say this is the way that light will behave in a gravitational field. And so that will give you a different curve. They are straight line in their geometry, but they are not straight line in Euclidean geometry.
Okay, yeah, great. Thank you.
Okay. Any other questions? All right, okay. So if not, we'll meet again on Wednesday. So I want to again stress that Friday is a holiday. Next week, Monday is a holiday, Canadian Thanksgiving. So Wednesday is the next class for this week, and we'll again meet next week, Wednesday. Okay, all right.
Thank you.
See, all right, bye-bye.
Thank you.
Thank you.
Thank you.